Tonight, we're going to explore something that will fundamentally change how you think about empty space. Because here's the thing, there is no such thing as empty space. What you think of as nothing, the vacuum, the void between atoms, the gaps between stars, it isn't empty at all. It's alive. It's buzzing with energy. It has structure. It has rules. And if you could somehow remove every single particle from a region of space, strip away every atom, every photon, every last trace of matter and radiation, what you'd be left with wouldn't be nothing. It would be something. Something with measurable energy. Something that physicists have confirmed in laboratories. Something so strange that even the scientists who study it struggle to fully explain what it means. And by the end of tonight, you're going to understand why. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's begin with something you've probably believed your entire life without ever questioning it. You've been taught, either explicitly or implicitly, that the universe is made of stuff. Particles. Little tiny objects flying around in empty space. Atoms are made of protons, neutrons, and electrons. Protons and neutrons are made of quarks, and all of these things exist as tiny solid objects, almost like microscopic billiard balls, moving through a void. Space is the stage. Particles are the actors. The stage itself is empty and passive. It just sits there while the particles do interesting things on top of it. This picture is intuitive. It feels right. It's the way most of us were taught to think about the physical world, starting in school and reinforced by nearly every popular description of physics you've ever encountered. Diagrams show little spheres orbiting other little spheres. Models on desks have colored balls connected by sticks. Even professional physicists sometimes draw particles as dots moving along lines. And this picture works remarkably well for everyday purposes. If you want to understand chemistry, you can think of atoms as little objects that bond together. If you want to understand why a table is solid, you can think of atoms packed tightly in a lattice. The billiard ball picture is useful, but it's wrong. Not slightly wrong, not approximately wrong, fundamentally wrong. The universe doesn't work that way at all. And the real picture, the one that physicists have spent the last century uncovering, is so different from what most people imagine that it changes everything about how you should think about space, matter, and what it means for something to exist. Because here's the truth. The universe is not made of particles moving through empty space. The universe is made of fields, continuous, invisible, all-pervading fields that stretch across every point in the cosmos. And particles, those little objects you were taught to think of as the building blocks of everything, are not fundamental. They're not the starting point. They're not the bedrock. Particles are what happens when a field gets disturbed. They're ripples, vibrations, temporary excitations in something much deeper and much more permanent. The fields are the real thing. The particles are just what the fields do. Now, I know that sounds abstract, so let me build this up carefully. Because understanding fields is the key to understanding everything that comes after. It's the key to understanding why empty space isn't empty, why the vacuum has energy, why nothingness has structure. All of it flows from this one idea: fields. Let's start with something familiar. Think about temperature in a room. At every point in that room, there's a temperature. Near the window on a cold day, the temperature might be lower. Near the heater, it's higher. In the middle of the room, it's somewhere in between. You don't need to place a thermometer at every location to know this. The temperature exists everywhere in the room simultaneously. It varies smoothly from point to point. If you wanted to describe the temperature of the entire room completely, you'd need to specify a number at every single point. That collection of numbers, one for every point in space, is what physicists call a field, a temperature field. This isn't exotic physics. It's something you experience constantly. The air pressure around you right now is a field. At every point in the atmosphere, there's a pressure value. Near the ground, pressure is higher. At high altitude, it's lower. It changes smoothly from place to place. Wind is a field. At every point in the atmosphere, the air has a speed and a direction. Ocean currents are fields. At every point in the ocean, the water is moving in some direction at some speed. Fields are everywhere in everyday life. They're just quantities that have a value at every point in space. Now, here's where things get deeper. In physics, some of the most important fields aren't things you can feel directly like temperature or wind. They're more fundamental. Gravity, for instance, can be described as a field. At every point in space, there's a gravitational field that tells you how strong gravity is and which direction it pulls. Near the surface of Earth, the gravitational field points downward and has a certain strength. Farther from Earth, the field gets weaker. Near the Sun, it's much stronger. This gravitational field exists everywhere. It fills all of space. It's not something that only exists where planets and stars are. It extends outward in every direction, getting weaker with distance, but never quite reaching zero. Every object with mass creates a gravitational field that stretches out to infinity, getting fainter and fainter, but never truly disappearing. The electromagnetic field is another example, and this one is crucial because it's going to connect directly to what we're exploring tonight. At every point in space, there's an electromagnetic field. This field describes the electric and magnetic forces that charged particles experience. When you turn on a light, you're creating a disturbance in the electromagnetic field. That disturbance travels outward at the speed of light. When it reaches your eyes, your retinas respond and you see light. The light isn't a separate thing traveling through an empty void. It's a ripple in the electromagnetic field, a vibration, a wave moving through something that fills all of space. This is where classical physics already starts to shift your picture of reality. Even before quantum mechanics entered the story, physicists in the 19th century realized that light wasn't a particle flying through emptiness. It was a wave in a field. James Clerk Maxwell showed in the 1860s that electric and magnetic phenomena could be unified into a single electromagnetic field, and that disturbances in this field traveled at the speed of light. Light was revealed to be an electromagnetic wave, not a thing moving through nothing, but a disturbance in something that was already everywhere. But classical fields like temperature and electromagnetic waves are smooth and continuous. They can have any value, they can carry any amount of energy. You can make a wave as small as you like, carrying as little energy as you want. There's no minimum, no granularity, no smallest possible disturbance. Quantum mechanics changed all of that, and the change was revolutionary. The first crack in the classical picture appeared in 1900, when Max Planck was trying to solve a problem about how hot objects radiate energy. Classical physics predicted that a hot object should radiate infinite energy at high frequencies, which was obviously absurd. Planck found that the only way to make the mathematics work was to assume that the electromagnetic field couldn't carry just any amount of energy. The energy had to come in discrete chunks, proportional to the frequency. He called these chunks quanta. It was a mathematical trick that he himself wasn't entirely comfortable with, but it worked. 5 years later, in 1905, Albert Einstein took Planck's idea further. He showed that light itself behaves as if it comes in discrete packets, which we now call photons. Einstein used this to explain the photoelectric effect, the observation that light shining on a metal surface ejects electrons, but only if the light's frequency is above a certain threshold. The energy of each packet depends on the frequency, not the brightness. This was one of the first clear signs that fields are quantized at the deepest level. In the early 20th century, physicists discovered something remarkable. When you look at fields at the smallest scales, at the level of atoms and subatomic processes, the smooth classical picture breaks down. Fields aren't continuous at the deepest level, they're quantized. This means that the energy a field carries comes in discrete packets. You can't have just any amount of energy in a field. You can have 1 unit, or 2 units, or 3, but not 1.5, not 2.25. The energy comes in whole number multiples of a fundamental unit. These discrete packets of field energy are what we call particles. Let me say that again because it's the most important idea in modern physics, and most people have never heard it stated this clearly. A particle is a discrete packet of energy in a quantum field. An electron isn't a tiny ball sitting in space. It's a quantized excitation of the electron field. A photon isn't a little pellet of light flying through the void. It's a quantized excitation of the electromagnetic field. A quark isn't a miniature marble rattling around inside a proton. It's a quantized excitation of the quark field. Every type of particle corresponds to a specific quantum field. There's an electron field that fills all of space. When that field is excited in a particular way, we observe an electron. There's a muon field. When it's excited, we observe a muon. There's a field for every type of quark, a field for every type of neutrino, fields for the W and Z bosons. The Higgs boson corresponds to excitations of the Higgs field. Gluons correspond to excitations of the gluon field. The entire zoo of fundamental particles that physicists have catalogued over decades corresponds to a collection of quantum fields, each one filling all of space, all of them layered on top of each other, coexisting everywhere simultaneously. Think of it like an ocean, a vast, calm ocean stretching in every direction. When the ocean is perfectly still, you don't see any waves, but the ocean is still there. The water exists. It has depth. It has properties. It has the capacity to support waves even when no waves are present. Now imagine you disturb the surface. You drop a stone. Ripples spread outward. Those ripples are real. They carry energy. They move across the surface, but they're not separate objects. They're not independent things that exist apart from the ocean. They are the ocean, moving in a particular way. The ripples are what the ocean does, not something added to the ocean from outside. Quantum fields are like that ocean, but far more profound. The electromagnetic field fills all of space like a vast, invisible ocean. When it's disturbed, when energy is added to it in the right way, we observe photons, ripples in the electromagnetic ocean. The electron field fills all of space like another ocean, overlapping with the first. When it's disturbed, we observe electrons, ripples in the electron ocean, and so on for every field. Space isn't empty with particles sprinkled through it. Space is filled with fields, and particles are what those fields look like when they're excited. This might sound like a subtle philosophical distinction, like we're just relabeling things. Calling a particle a field excitation instead of a little ball. What difference does it make? But it makes an enormous difference, and here's why. If particles were truly fundamental, if they were little independent objects, then removing all the particles from a region of space would leave you with nothing. Literally nothing. Empty space would be genuinely empty. There would be no physical reality there, no properties, no energy, no structure, just a void, an absence, a blank stage waiting for something to be placed on it. But if fields are fundamental, then removing all the particles doesn't remove the fields. The fields are still there. They're always there. You can't remove a quantum field from space any more than you can remove depth from the ocean. The field is part of what space is. It's woven into the fabric of reality itself. So when you remove every particle from a region of space, when you strip away every excitation, every ripple, what you're left with isn't nothing. You're left with the fields in their lowest energy state, their quietest configuration, their ground state. And that ground state, that quietest possible condition of the quantum fields, is what physicists call the vacuum. The vacuum isn't empty. It can't be empty, because the fields are still there. And as we're going to discover, those fields in their ground state still have energy, still have fluctuations, still have physical consequences that we can measure in laboratories. The vacuum is not nothing. It's something. Something subtle, something quiet, but absolutely something. Now, this idea that fields are more fundamental than particles isn't just a theoretical preference or a philosophical stance. It's the foundation of the most successful and precisely tested theory in all of physics. Quantum field theory. This is the mathematical framework that describes how quantum fields behave, how they interact, and how their excitations create the particles we observe. Quantum field theory underlies the standard model of particle physics, which describes all known fundamental forces except gravity. Every prediction of quantum field theory that has been tested experimentally has been confirmed. Some of these predictions have been verified to more than 10 decimal places of accuracy. There is no theory in the history of science that has been tested more rigorously or confirmed more precisely than quantum field theory. And at the heart of quantum field theory is this idea. Fields are the fundamental entities. They exist everywhere in space. Particles are excitations of those fields. And the vacuum, the state with no excitations, is not nothing. Let me give you a sense of just how many fields we're talking about. According to the standard model, space is filled with at least 17 distinct quantum fields. There's the electromagnetic field. There are 3 fields for the charged leptons, the electron field, the muon field, and the tau field. There are 3 neutrino fields. There are 6 quark fields, 1 for each flavor of quark. Up, down, charm, strange, top and bottom. There are the fields for the force carriers. the gluon field for the strong force, the W and Z boson fields for the weak force, and there's the Higgs field, which gives mass to other particles through their interaction with it. All of these fields exist simultaneously at every point in space. They overlap, they coexist, they interact with each other in complex ways, and every one of them is always present, always there, even when no particles are being produced. Right now, as you're hearing these words, every point in the space around you contains all of these fields. The electron field is there. The quark fields are there. The electromagnetic field is there. The Higgs field is there. You can't see them. You can't feel them directly, but they're there. And if conditions were right, if enough energy were concentrated at a point, any of these fields could be excited, producing the corresponding particle. The fields are always ready, always present, always capable. This is profoundly different from the old picture of empty space with particles scattered through it. In the old picture, a region of space either contains a particle or it doesn't. In the quantum field picture, the field is always there. What varies is whether the field is excited or not. A photon doesn't appear out of nothing. The electromagnetic field was already there, and something caused it to become excited. An electron doesn't materialize from the void. The electron field was already there, and energy was transferred into it, creating an excitation that we observe as an electron. This distinction matters enormously when we start asking questions about the vacuum. Because in the old picture, if you remove all the particles, you have nothing. But in the quantum field picture, if you remove all the excitations, you still have all the fields. And those fields in their ground state have properties that are anything but nothing. To understand this properly, we need to think about what it means for a quantum field to be in its lowest energy state. And this is where quantum mechanics introduces something that defies everyday intuition. Because in the classical world, the world of everyday experience, when something is in its lowest energy state, it's perfectly still. A ball at the bottom of a valley isn't moving. A pendulum hanging straight down isn't swinging. Everything is calm, settled, quiet. The energy is as low as it can possibly be, and there's no motion. But in quantum mechanics, this isn't possible. A quantum system cannot be perfectly still. It cannot have exactly zero motion. There's a fundamental limit built into the laws of physics that prevents any quantum system from settling into a state of absolute rest. This limit comes from one of the most important principles in all of quantum mechanics, the Heisenberg uncertainty principle. The reason comes from one of the deepest principles in quantum mechanics, that the Heisenberg uncertainty principle. We'll explore the details shortly, but the essential point is this. The uncertainty principle places a fundamental limit on how still any quantum system can be. There are certain pairs of physical properties that cannot both be precisely zero at the same time. For a quantum field, this means the field can never sit perfectly at rest. It must always retain some minimum level of activity, some irreducible jitter, even in its lowest energy state. The field fluctuates constantly, not by a lot. The fluctuations are tiny by everyday standards, but they're never zero. They can never be zero. And these fluctuations carry energy. The vacuum state of a quantum field isn't zero energy. It has a small but non-zero energy at every point in space. This is called zero-point energy. The energy that remains when you've cooled everything to absolute zero, removed every particle, eliminated every source of radiation, done everything conceivably possible to remove energy from a system, there's still energy left, because the fields cannot be still. The uncertainty principle guarantees it. And here's what makes this truly remarkable. This isn't happening for just one field, it's happening for every quantum field simultaneously. The electron field has 0-point fluctuations. The quark fields have 0-point fluctuations. The electromagnetic field has 0-point fluctuations. Every one of the 17 or more quantum fields filling space is fluctuating in its ground state, carrying a minimum amount of energy that can never be removed. The vacuum, what we casually call empty space, is therefore not empty at all. It's a seething, restless medium filled with the irreducible quantum fluctuations of every fundamental field in nature. It has energy, it has structure, it has physical consequences that we can detect and measure. And understanding these properties, understanding what the vacuum really is and why it behaves the way it does, is one of the deepest and most important questions in modern physics. Now, you might be wondering how we know any of this is real. How do we know that vacuum fluctuations actually exist? How do we know that 0-point energy isn't just a mathematical artifact, something that appears in the equations but doesn't correspond to anything in the physical world? These are fair questions, and the answers are compelling. Because the effects of vacuum fluctuations have been measured directly, in laboratories, multiple times, using different methods, and every single measurement confirms what quantum field theory predicts. There are experiments that have detected the force created by vacuum fluctuations between two metal plates. There are measurements of atomic energy levels that can only be explained if the vacuum is fluctuating. There are precision tests of particle properties that match theoretical predictions only when vacuum effects are included. The evidence is overwhelming and has been accumulating for more than 75 years, but we're getting ahead of ourselves. The details of these experiments and what they reveal about the vacuum are coming. For now, the crucial thing to understand is this foundational shift in how physics views reality. The universe is made of fields. Those fields are everywhere. Particles are temporary excitations of those fields. And the vacuum, the state with no particles, is not the absence of everything. It's the lowest energy state of the fields. A state that still has energy, still has fluctuations, still has physical structure. This is where the journey truly begins. Because once you accept that the vacuum is not nothing, once you understand that empty space is actually filled with quantum fields and their ground state, the questions start multiplying. How much energy does the vacuum contain? What do the fluctuations actually look like? Can we measure them? Can we use them? What role did the vacuum play in the birth of the universe? Could the vacuum itself be unstable? Could it change? These are not idle philosophical questions. They're real physics questions with real experimental consequences, and some of the most profound implications in all of science. The nature of the vacuum connects to the origin of the universe, the fate of the cosmos, the mystery of dark energy, and some of the biggest unsolved problems in physics. Everything starts here, and the quietest, most stripped down state of reality still contains energy, structure, and the seeds of everything that exists. The vacuum is not a void, it's a foundation, and we're about to discover just how much it contains. So now we know that space is filled with quantum fields, not one field, but many. at least 17 fundamental quantum fields, all layered on top of each other, all stretching across every point in the universe. And we know that particles aren't separate little objects. They're excitations of these fields, ripples, vibrations, temporary disturbances in something much deeper and much more permanent. But now we need to ask a more specific question. A harder question. What exactly is the vacuum state? What does it mean precisely for a quantum field to be in its lowest energy configuration? And why does that state still contain energy? Let me start with an analogy that helps make this concrete. Think about a guitar string. When you pluck a guitar string, it vibrates. It oscillates back and forth, producing a sound wave. The vibration carries energy. The louder the sound, the more energy the string carries. This is like a quantum field being excited. The vibration of the string is like a particle. It's the field doing something, carrying energy, producing an observable effect. Now, stop plucking the string. Let it settle down. Eventually the vibration dies away. The sound fades, the string returns to rest. It sits there on the guitar, still and silent. No vibration, no sound, no energy of oscillation. But the string is still there. It hasn't disappeared. It still has tension. It still has mass. It still has all the physical properties that would allow it to vibrate again if you plucked it. The string in its resting state isn't nothing. It's something. It's a string that happens to not be vibrating right now. And if you were to pluck it again, it would vibrate immediately because all the necessary structure is already in place. The quantum vacuum is like the unplucked string. When a quantum field is in its vacuum state, there are no particles present, no excitations, no ripples. The field isn't doing anything dramatic, but the field is still there. It hasn't disappeared. It still has all the properties that would allow particles to be created if energy were added. The vacuum state is the field at rest, not the absence of the field, just the field in its quietest, lowest energy configuration. But here's where the analogy breaks down in a crucial way. A classical guitar string can truly be at rest. It can sit perfectly still with zero vibration and zero energy of oscillation. In classical physics, a system can reach a state of complete stillness, absolute zero motion, total calm. A quantum field cannot do this, and the reason it can't is one of the most important and counterintuitive facts in all of physics. It comes down to the Heisenberg uncertainty principle, and the way it applies to fields is what gives the vacuum its remarkable properties. We touched on the uncertainty principle briefly before, but now we need to dig deeper because this is the engine that drives everything. Werner Heisenberg formulated his uncertainty principle in 1927, and it describes a fundamental limitation built into the structure of quantum mechanics. Certain pairs of physical quantities are conjugate to each other, meaning they're linked by a mathematical relationship that prevents both from being precisely defined at the same time. The most famous pair is position and momentum. If you know exactly where a particle is, you cannot simultaneously know exactly how fast it's moving. And this isn't about measurement limitations. It's not that your ruler isn't precise enough, or your stopwatch isn't fast enough. The particle itself doesn't have a definite momentum when its position is perfectly defined. The universe genuinely doesn't contain that information. Reality at the quantum level is inherently fuzzy in a way that no amount of technological improvement can overcome. For quantum fields, the relevant pair of conjugate quantities is the field value and its rate of change at a given point. Think of it this way. At any point in space, a quantum field has some value. You can think of this as how far the field is displaced from its equilibrium, like how far a spring is stretched from its natural length. The field also has a rate of change, which describes how quickly that value is shifting at that moment. It's analogous to the velocity of the spring. The uncertainty principle tells us that both of these quantities cannot simultaneously be exactly zero. If the field value were pinned precisely to zero, then its rate of change would be completely undetermined, meaning it could be anything. And if the rate of change were pinned to zero, the field value would be completely undetermined. For both to be exactly zero simultaneously, for the field to be perfectly still, with no displacement and no tendency to change, would violate the uncertainty principle. This means that even in the lowest possible energy state, the quantum field must retain some minimum level of activity. It cannot sit perfectly at zero. It must jitter. It must fluctuate. Not because something is disturbing it from outside, not because it's receiving energy from somewhere, but because the mathematical structure of quantum mechanics forbids absolute stillness. The fluctuations are intrinsic. They're built into what it means to be a quantum system. Let me make this more precise using a concept from physics called the quantum harmonic oscillator, which is one of the most important models in all of quantum mechanics. Don't let the name intimidate you. The idea is straightforward. A harmonic oscillator is just anything that vibrates back and forth around a central point. A weight on a spring, a pendulum swinging through small angles, a child on a swing. These are all harmonic oscillators. They oscillate back and forth with a characteristic frequency, a natural rhythm that depends on the properties of the system. In classical physics, you can reduce the energy of a harmonic oscillator as much as you want. You can slow the pendulum down gradually until it's barely moving, and then slow it down further until it stops completely. At that point, it has zero energy of oscillation. It's perfectly still. This is the classical ground state. Zero energy, complete rest. In quantum mechanics, this doesn't work. When you solve the equations for a quantum harmonic oscillator, when you apply the rules of quantum mechanics to a simple vibrating system, you find that the lowest possible energy is not zero. It's 1/2 times the fundamental energy unit of the system. Physicists write this as 1/2 times h bar times omega, where h bar is the reduced Planck constant and omega is the natural frequency of the oscillator. The exact formula doesn't matter for our purposes. What matters is the conclusion. The lowest energy is not zero. It's half of a fundamental unit. No matter what you do, no matter how much energy you remove, you can never get below this minimum. The system always retains this residual energy, this 1/2 quantum of vibration. This residual energy is the 0 point energy. It's called that because it persists even at absolute zero temperature, even when you've removed all thermal energy from the system, even when there's nothing left to remove. The half quantum of energy remains because the uncertainty principle demands it. The oscillator cannot be perfectly still, so it must retain this minimum vibration, and that vibration carries energy. Now here's where things get powerful. A quantum field can be thought of as a collection of quantum harmonic oscillators. Not one oscillator, but infinitely many. At every point in space, the field has a value that can oscillate, just like a tiny spring at every location. Each of these oscillators has its own frequency. Some vibrate quickly, some slowly, and every single one of them, in the vacuum state, retains its half quantum of 0-point energy. Think about what this means. At every single point in space, for every quantum field, there are oscillators at every possible frequency, and each one contributes a half quantum of energy to the vacuum. The electromagnetic field has 0-point energy at every point. The electron field has 0-point energy at every point. Every quark field, every neutrino field, the Higgs field, all of them are contributing 0-point energy at every location in space. The vacuum state isn't a state of zero energy, it's a state of minimum energy. And that minimum is not zero. It's the sum of all the half quanta from all the oscillators of all the fields at every point in space. This energy is real. It's not an accounting trick. It's not an artifact of the mathematics that can be subtracted away and ignored. It has physical consequences that we can detect and measure. And the most direct, most dramatic demonstration of this is an experiment that has been performed in laboratories around the world. It's called the Casimir effect. The Casimir effect was first predicted in 1948 by the Dutch physicist Hendrik Casimir. His prediction was remarkable because it said that two uncharged, perfectly conducting metal plates placed very close together in a vacuum would experience a measurable force pushing them together. Not an electrical force, not a magnetic force, not gravity, a force arising purely from the vacuum itself. Here's how it works, and it's beautifully simple in concept. Imagine two flat metal plates placed parallel to each other with a very small gap between them. Tiny. We're talking about a gap measured in micrometers, millionths of a meter. Now, remember that the vacuum is filled with fluctuations of the electromagnetic field at every possible wavelength. Outside the plates, in the open space, the electromagnetic field can fluctuate at any wavelength. There are no restrictions. Every possible mode of vibration is available. But between the plates, the situation is different. The conducting plates impose a boundary condition. They require that the electromagnetic field essentially vanishes at their surfaces. This means that only certain wavelengths of fluctuation can fit between the plates. Wavelengths that fit an exact whole number of half waves into the gap. All other wavelengths are excluded. They simply cannot exist in that confined space. Think of it like a vibrating string fixed at both ends. A guitar string can vibrate at its fundamental frequency, where one half wave fits between the two fixed points. It can vibrate at the second harmonic, where two half waves fit, the third harmonic, where three half waves fit, and so on. But it cannot vibrate at wavelengths that don't fit between the fixed points. The boundary conditions restrict which vibrations are possible. The same thing happens with the electromagnetic field between the Casimir plates. Only fluctuations with wavelengths that fit the gap are allowed, and crucially, the longer the wavelength, the less likely it is to fit. Wavelengths longer than twice the gap width are completely excluded. This means that between the plates, there are fewer vacuum fluctuations than in the open space outside. The total 0-point energy per unit volume is lower between the plates than outside. And this difference in energy creates a force. The energy density outside the plates is higher than between them. This imbalance pushes the plates together. It's as if the vacuum fluctuations outside the plates are exerting more pressure than the fluctuations between them. The plates get squeezed together by the vacuum itself. This force is tiny, incredibly tiny. For plates separated by about 1 micrometer, the Casimir force is roughly equivalent to the weight of a fraction of a millionth of a gram spread over a square centimeter. You could never feel it. You could never see its effects with the naked eye. But it's there. And we can measure it. The first precise measurement of the Casimir effect was performed in 1997 by Steve Lamoureux at the University of Washington. He used a torsion pendulum, one of the most sensitive force measuring instruments available, to detect the force between a gold-plated sphere and a flat gold-plated plate. His results matched Casimir's prediction to within 5%. Since then, the experiment has been repeated many times with increasing precision by research groups around the world. Modern measurements confirm the Casimir effect to within about 1% accuracy. The technical difficulty of measuring the Casimir effect cannot be overstated. The force is so tiny that any stray electric charge on the plates, any slight surface roughness, any vibration from the building or the street outside would completely overwhelm the signal. Lamoureux had to work in carefully shielded environments, controlling for electrostatic forces that could mimic the Casimir effect. The surfaces of his gold-coated plates had to be smoothed to within nanometers. Even the geometry mattered. He used a sphere and a flat plate, rather than 2 flat plates, because aligning 2 perfectly parallel flat surfaces at micrometer separations is nearly impossible. Any slight tilt would change the distance across the surface, smearing out the force. The sphere plate geometry is more forgiving because the distance varies smoothly. Every subsequent experiment has faced similar challenges, and the steady improvement in precision over the decades reflects extraordinary advances in nanofabrication and vibration isolation. The vacuum really does exert a measurable force on physical objects. Let me emphasize how remarkable this is. You take 2 metal plates, you place them in a vacuum. There's nothing between them. No particles, no radiation, no fields in an excited state, just empty space. And yet, the plates are pushed together by a real, measurable, physical force. The only explanation is that the empty space between them isn't truly empty. It contains vacuum fluctuations of the electromagnetic field, and those fluctuations are restricted by the plates in a way that creates a pressure difference. The Casimir effect is direct, physical, laboratory-confirmed evidence that the vacuum has energy and structure. It's not theoretical speculation. It's not philosophy. It's measured fact. The vacuum does something. It exerts forces on physical objects. And it does this because the quantum fields filling space have 0-point fluctuations that carry real energy. Now, the Casimir effect demonstrates vacuum energy indirectly through the difference in fluctuations between 2 regions of space. But what about the total amount of vacuum energy? What happens if you try to add up all the 0-point energy from all the quantum fields at every point in space? This is where things get truly strange, and where one of the biggest puzzles in all of physics emerges. Remember, at every point in space, every quantum field contributes 0-point energy from oscillators at every possible frequency. In principle, there's no upper limit on frequency. Oscillators can vibrate at higher and higher frequencies without bound, and each one contributes its half quantum of energy. If you naively add up all these contributions, summing over all frequencies for all fields at every point, the total energy you get is infinite. Obviously, that can't be right. An infinite energy density at every point in space would have catastrophic gravitational effects. According to Einstein's general theory of relativity, energy curves space-time. Energy creates gravity. If the vacuum had infinite energy density, the universe would curve in on itself instantaneously. It would collapse. Nothing would exist. Clearly, something is wrong with the naive calculation. Physicists handle this in practice by using a technique called renormalization. They argue that what matters physically is not the absolute value of the vacuum energy, but differences in energy between states. When you calculate the Casimir effect, you're calculating the difference in vacuum energy between the region between the plates and the region outside. That difference is finite, well-defined, and matches experiment. The infinite total can be set aside because only differences are observable. This works beautifully for calculating specific physical effects. The Casimir force, atomic energy shifts, particle properties, all of these can be computed by looking at energy differences and ignoring the absolute value of the vacuum energy. And the results match experiments with extraordinary precision. But there's a problem. A deep, fundamental, unsolved problem. Because gravity doesn't care about energy differences. Gravity responds to the total energy. According to general relativity, all energy, including vacuum energy, curves space-time and contributes to the expansion or contraction of the universe. The absolute value of the vacuum energy matters for cosmology. You can't just ignore it. So physicists tried to make a more reasonable estimate. Instead of summing to infinite frequency, they imposed a cutoff. They assumed that the calculation should only include frequencies up to some maximum, typically the Planck scale, which is the energy scale where quantum gravity effects are expected to become important. The Planck energy is enormous, trillions of times greater than the energy released in a typical nuclear reaction. When you sum the 0-point energies of all fields up to this cutoff, you get a finite but staggeringly large number. How large? The predicted vacuum energy density comes out to roughly 10 to the 113 joules per cubic meter. That's a 1 followed by 113 zeros. This is an almost inconceivably enormous energy density. Now, we actually have an observational measure of the vacuum energy density. We can infer it from the observed expansion rate of the universe. In 1998, 2 independent teams of astronomers, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, discovered that the expansion of the universe is accelerating. Something is pushing the universe apart, causing galaxies to recede from each other faster and faster. This something behaves exactly like a constant energy density pervading all of space. It's consistent with what you'd expect from vacuum energy. The observed value of this dark energy, as it's now called, corresponds to an energy density of roughly 10 to the negative 9 joules per cubic meter. That's a tiny number. Incredibly tiny. A decimal point followed by 9 zeros, and then a 1. It's barely anything. Compare the two numbers. The theoretical prediction from quantum field theory gives 10 to the 113 joules per cubic meter. The observed value from cosmology gives 10 to the negative 9 joules per cubic meter. The discrepancy between these two numbers is roughly 120 orders of magnitude. That's a factor of 10 to the 120th power. A 1 followed by 120 zeros. This is not a small disagreement. This is arguably the worst prediction in the history of physics. The theoretical prediction overshoots the observed value by a factor so enormous that the human mind cannot meaningfully process it. It's as if you predicted that a glass of water would weigh more than the observable universe. The numbers aren't just different, they're different on a scale that defies comprehension. This problem is known as the cosmological constant problem, and it has haunted physics for decades. It was first clearly articulated in the 1980s, and despite enormous effort by some of the brightest minds in theoretical physics, no satisfactory solution has been found. There are several possible responses to this problem. One is that we're calculating the vacuum energy wrong. Maybe there's some mechanism, some principle we haven't discovered yet that cancels most of the vacuum energy, leaving only the tiny residual amount we observe. Supersymmetry, a theoretical framework that proposes a symmetry between particles with different spin properties, provides a partial mechanism for such cancellation. In a supersymmetric theory, the zero-point contributions from certain types of fields cancel against contributions from others. But supersymmetry, even if it exists, is clearly not an exact symmetry in our universe because the cancellation would need to be nearly perfect. And even a small mismatch would leave a vacuum energy far larger than what's observed. Another response involves what's called the anthropic principle. In some theoretical frameworks, particularly those involving the string theory landscape, the vacuum energy can take different values in different regions of a multiverse. Most values would be incompatible with the existence of complex structures like galaxies, stars, and life. We find ourselves in a region where the vacuum energy happens to be small enough for structure to form and for observers like us to exist. We don't observe the typical value. We observe a value that's compatible with our existence. This is controversial. Many physicists consider it unsatisfying because it doesn't provide a mechanism. It just says we're in a lucky region without explaining why the vacuum energy takes the specific value it does. A third possibility is that the vacuum energy really is large, but that gravity doesn't respond to it in the way general relativity predicts. Maybe our theory of gravity needs modification at cosmological scales. This approach has motivated various modified gravity theories, but none has yet succeeded in solving the cosmological constant problem while remaining consistent with all other observations. The honest answer is that nobody knows. The cosmological constant problem remains open. It's one of the deepest and most important unsolved problems in physics. It sits at the intersection of quantum mechanics and gravity, the two pillars of modern physics that we still don't know how to unify. Many physicists believe that solving the cosmological constant problem will require a theory of quantum gravity, a framework that combines quantum mechanics and general relativity into a single coherent theory. We don't have such a theory yet. String theory, loop quantum gravity, and other approaches are candidates, but none has been experimentally confirmed. What we do know is this: the vacuum has energy. That energy is real. We can measure its effects in the laboratory through the Casimir effect and other phenomena. The vacuum is not nothing. It has physical properties, including an energy density that contributes to the behavior of the universe. But the exact value of that energy density, the reason it has the specific small value we observe rather than the enormous value quantum field theory naively predicts, remains a mystery. A mystery that connects the physics of the very small quantum fields and their fluctuations to the physics of the very large, the expansion and fate of the entire cosmos. The vacuum state, the quietest possible configuration of the quantum fields that fill all of space, turns out to be one of the most profound and puzzling objects in all of physics. It's not empty. It's not simple. It's not fully understood. It's a state with residual energy, with fluctuations that cannot be removed, with physical consequences that we can detect, and with properties that connect to the deepest unsolved problems in science. And we're just getting started. Because those fluctuations, those tiny quantum jitters in the vacuum state, do more than create forces between metal plates and confuse cosmologists. They actively participate in the physics of real particles. They shift energy levels. They alter magnetic properties. They interact with matter in ways that have been measured with breathtaking precision. And under extreme conditions, near black holes and in the earliest moments of the universe, the vacuum does things that are truly extraordinary. The vacuum isn't just quietly humming in the background. It's doing things. Real, measurable, consequential things. And we're about to explore exactly what those things are. So far, we've established two fundamental ideas. First, that space is filled with quantum fields, invisible and continuous, stretching across every point in the universe. Second, that these fields in their lowest energy state, the vacuum state, still retain energy, 0-point energy, a residual hum of activity that the uncertainty principle refuses to let go silent. We've seen that this energy is real, that it creates measurable forces between metal plates, and that its total value presents one of the greatest unsolved puzzles in all of physics. But now we need to go deeper. Because the vacuum doesn't just have energy, it does things. The quantum fluctuations of the vacuum aren't just passively sitting there, carrying energy but not interacting with anything. They actively participate in physical processes. They shift the energy levels of atoms. They alter the magnetic properties of electrons. And under extreme conditions, they can produce real, detectable particles from what appears to be nothing. The vacuum is not a quiet backdrop to the drama of the physical world. It's one of the actors, and its role is far more important than most people realize. Let's start by getting more precise about what vacuum fluctuations actually are, because this is a topic surrounded by widespread misunderstanding. You've probably heard the popular description. In the quantum vacuum, pairs of virtual particles constantly pop into existence from nothing, exist for a brief moment, and then annihilate each other and disappear. A virtual electron and a virtual positron appear, exist for an unimaginably short time, and then collide and vanish. This happens everywhere, all the time, throughout all of space. The vacuum is a seething foam of particle-antiparticle pairs winking in and out of existence. This description is everywhere. It's in popular science books, documentaries, magazine articles, and YouTube videos. It's one of the most commonly repeated descriptions of quantum physics in popular culture. And while it captures something true about the mathematics, as a literal description of what's happening in the vacuum, it's deeply misleading. Here's the problem. The phrase particles popping into existence from nothing suggests that actual particles, real physical objects with definite positions and momenta, are materializing out of the void, hanging around for a moment, and then disappearing. As if the vacuum is constantly manufacturing little bits of matter and antimatter, and then destroying them. As if there's a factory in empty space that runs perpetually, creating and annihilating particles at a frantic pace. That's not what's happening. What's actually happening is both subtler and more profound. Remember what we established earlier. Quantum fields fill all of space. These fields have values at every point. And the uncertainty principle prevents those values from being perfectly still, even in the vacuum state. The fields fluctuate, they jitter, their values shift randomly around zero, never quite settling down. These fluctuations are not particles, they're fluctuations in the field itself. They're variations in the value of the quantum field at different points in space and time. The field doesn't create particles and then destroy them. The field just fluctuates. It trembles in a way that quantum mechanics mandates. So where does the virtual particle language come from? It comes from a specific mathematical technique used to calculate the effects of these fluctuations. The technique was developed primarily by Richard Feynman in the late 1940s and involves what are now called Feynman diagrams. These are pictorial representations of mathematical calculations. They show lines representing particles interacting with each other, and the internal lines in these diagrams, the ones that don't correspond to incoming or outgoing particles, are called virtual particles. But here's the crucial thing. Feynman diagrams are calculation tools. They're a way of organizing very complex mathematics into manageable pieces. Each diagram represents a term in an infinite mathematical series. When you add up the contributions from all the diagrams, you get the answer to your calculation. The virtual particles in these diagrams are mathematical terms, not physical objects. They're part of the accounting, not part of the physics. An analogy might help. Imagine you're trying to calculate the total amount of water that flows through a complex network of rivers and tributaries. You might break the problem into pieces. Calculate the flow through one channel, then another. Then account for how they merge and split. Each piece of your calculation involves a specific pathway of water. But those pathways aren't real rivers. They're just how you organized your math. The real physical thing is the total flow of water through the network, not the individual pathways you invented for your calculation. Similarly, virtual particles are the pathways of a calculation. They're not real particles that actually exist in the vacuum. The real physical thing is the total effect of the vacuum fluctuations on whatever system you're studying. That total effect is real and measurable. But the individual virtual particles that appear in the calculation are mathematical fictions. Useful mathematical fictions, indispensable for getting the right answer, but fictions nonetheless. This distinction matters because the virtual particle picture leads to misconceptions. It makes people think that energy is somehow being created and destroyed in the vacuum, that conservation of energy is being violated, that particles are being manufactured from nothing. None of this is true. The vacuum fluctuations are simply the inherent quantum uncertainty in the field values. They don't violate energy conservation. They don't create matter from nothing. They're just the fields doing what quantum mechanics requires them to do, fluctuating at their minimum possible level. Now, having carefully explained what vacuum fluctuations are and are not, let's talk about what they do. Because even though virtual particles aren't literally real, the effects of vacuum fluctuations absolutely are. And those effects have been measured with spectacular precision. The first major experimental confirmation came in 1947, and it involved something called the Lamb shift. This discovery shook the foundations of theoretical physics and launched an entirely new era in our understanding of quantum fields. To understand the Lamb shift, you need to know a little about hydrogen atoms. Hydrogen is the simplest atom in the universe. 1 proton, 1 electron. That's it. Because it's so simple, physicists can calculate its properties with great precision. The energy levels of hydrogen, the specific energies at which the electron can orbit the proton, were calculated using quantum mechanics in the 1920s by Paul Dirac. Dirac's equation, which combined quantum mechanics with special relativity, predicted the energy levels of hydrogen with remarkable accuracy. It was one of the great triumphs of theoretical physics. But Dirac's equation made a specific prediction that turned out to be very slightly wrong. According to Dirac's theory, 2 particular energy levels of hydrogen, called the 2s1/2 and 2p1/2 states, should have exactly the same energy. This is because both states have the same quantum numbers in Dirac's framework. They should be degenerate, meaning identical in energy. In 1947, Willis Lamb and Robert Rutherford performed a precision measurement of these energy levels using microwave spectroscopy. What they found was that the 2 levels were not identical. The 2s1/2 state had slightly higher energy than the 2p1/2 state. The difference was tiny, corresponding to a frequency of about 1057 MHz. Incredibly small by everyday standards, but clearly measurable with their equipment, and clearly different from zero. This was a crisis for theoretical physics. Dirac's equation was the best theory available, and it predicted no energy difference. The measurement said otherwise. Something was missing from the theory. The crisis was deeper than a single wrong prediction. Physicists had known for years that there were problems with combining quantum mechanics and special relativity when applied to electromagnetic interactions. Every time they tried to calculate certain quantities, like the self-energy of the electron, the answer came out as infinity. Not a large number. Literally infinity. The electron interacting with its own electromagnetic field produced an infinite correction to its energy. This was a disaster. Infinities in physics usually mean your theory is broken. Many of the greatest minds of the 1930s and 40s struggled with this problem. Some thought quantum electrodynamics was fundamentally flawed and needed to be replaced entirely. Paul Dirac himself believed the theory had deep structural problems that might require starting over from scratch. Lamb's measurement changed the atmosphere completely. It gave physicists a specific, finite, measurable number that the theory had to reproduce. It transformed the infinity problem from an abstract mathematical headache into a concrete experimental challenge. The theory had to give the right answer for the Lamb shift, and that meant finding a way to tame the infinities. This urgency led directly to the breakthrough. The resolution came almost immediately. Hans Bethe, on a train ride from a conference where Lamb presented his results, performed a rough calculation and showed that the energy shift could be explained by the interaction between the hydrogen electron and the vacuum fluctuations of the electromagnetic field. Here's what's happening physically. The electron in a hydrogen atom isn't sitting in a perfectly smooth, calm electromagnetic field. It's sitting in a field that's fluctuating. The vacuum fluctuations of the electromagnetic field are constantly jittering, and the electron responds to these jitters. The electron gets buffeted by the vacuum fluctuations, causing it to wobble slightly around its average position. This wobbling means the electron samples a slightly different region of the proton's electric field than it would if the vacuum were perfectly calm, and this slight difference in the effective electric field experienced by the electron shifts the energy levels by a tiny amount. The key insight is that the two states, 2s1/2 and 2p1/2, are affected differently by this wobbling. The 2s1/2 state has a wave function that's concentrated closer to the proton, where the electric field is stronger. The wobbling caused by vacuum fluctuations matters more there because the field changes more rapidly over small distances. The 2p1/2 state has its wave function distributed differently, and the vacuum fluctuations affect it less. The result is that the two states, which Dirac's theory said should have the same energy, actually have slightly different energies when you account for the vacuum. Bethy's initial calculation was rough, but it gave the right order of magnitude. Over the following months and years, more precise calculations using the full machinery of quantum electrodynamics confirmed the result. The theoretical prediction for the Lamb shift, calculated by including the effects of vacuum fluctuations, matched the experimental measurement with extraordinary precision. The Lamb shift was one of the pivotal moments in 20th century physics. It demonstrated that the vacuum fluctuations predicted by quantum field theory were not just mathematical curiosities. They had real, measurable effects on physical systems. The vacuum was actively influencing the behavior of atoms. This realization helped drive the development of quantum electrodynamics into the precise, powerful theory it is today. But the Lamb shift was just the beginning. An even more dramatic confirmation of vacuum fluctuation effects came from measurements of the electron's magnetic properties. Every electron behaves like a tiny magnet. It has a property called a magnetic moment, which describes how strongly it interacts with magnetic fields. The simplest version of quantum theory, Dirac's equation, predicts a specific value for this magnetic moment. Physicists express the magnetic moment in terms of a number called the G factor. Dirac's equation predicts that the G factor of the electron should be exactly 2, but measurements showed that it's not exactly 2. It's slightly more than 2. The difference is tiny, about 0.00116, but it's definitely there. This tiny deviation from 2 is called the anomalous magnetic moment of the electron, and its explanation once again involves vacuum fluctuations. The electron doesn't exist in isolation. It's constantly interacting with the quantum fields around it, including the fluctuating vacuum. These interactions slightly modify the electron's effective magnetic properties. The electron, as it moves through space, is surrounded by a cloud of vacuum fluctuations. It interacts with fluctuations in the electromagnetic field, in the electron-positron field, in the fields of the weak force, and even indirectly with the strong force through quark and gluon field fluctuations. All of these interactions contribute tiny corrections to the electron's magnetic moment. Calculating these corrections is extraordinarily difficult. You have to sum up contributions from thousands of Feynman diagrams, each one representing a different way the electron can interact with the vacuum. The calculations took decades to complete and required some of the most sophisticated mathematical techniques ever developed in physics. But when the final theoretical prediction was compared to the measured value, the agreement was staggering. The theoretical prediction and the experimental measurement of the electron's anomalous magnetic moment agree to more than 10 significant figures. More than 10 decimal places. Getting to that level of agreement required one of the most sustained and painstaking computational efforts in the history of physics. The calculation involves summing contributions from Feynman diagrams of increasing complexity. The first correction, involving a single virtual photon loop, was calculated by Schwinger in 1948. It gives a correction of about 0.00116. That's pretty close to the measured value, but not close enough for physicists. The next level of correction involves diagrams with two loops. There are 7 of them. They were calculated by the late 1950s. Then 3-loop diagrams. There are 72 of them. These took until the 1990s to compute. Then 4-loop diagrams. There are 891 of them. These required supercomputers and took a team led by the Japanese physicist Toichiro Kinoshita, decades of meticulous work. The 5-loop contribution involves over 12,000 diagrams. Kinoshita and his collaborators spent years developing computer algorithms to evaluate them. Each diagram requires complex multi-dimensional integrals that push the limits of numerical computation. And every single one of these contributions matters if you want to match the experimental precision. The fact that the sum of all these contributions, thousands of diagrams at multiple levels of complexity, converges to a number that matches experiment to more than 10 decimal places is nothing short of astonishing. Let me put that in perspective. If you measure the distance from New York to Los Angeles, a distance of about 4,500 kilometers, with an accuracy of 10 significant figures, you'd be accurate to within a fraction of a millimeter. That's the level of agreement between theory and experiment for the electron's magnetic moment. This is often cited as the most precise prediction in all of science. And it's a prediction that crucially depends on vacuum fluctuations. Without accounting for the interactions between the electron and the fluctuating vacuum, the theoretical prediction would be wrong. The vacuum isn't just a passive stage, it's actively modifying the properties of every electron in the universe, and we can calculate those modifications with precision that matches experiment to more than 10 decimal places. Think about what this means. The vacuum, this seemingly empty space that appears to contain nothing, is influencing the fundamental properties of matter in ways that we can predict and verify with the highest precision ever achieved in experimental science. The agreement between theory and experiment for the anomalous magnetic moment isn't just good evidence that vacuum fluctuations exist. It's overwhelming evidence. It's about as strong as scientific evidence can possibly be. These two results, the Lamb shift and the anomalous magnetic moment of the electron, are the crown jewels of quantum electrodynamics. They demonstrate beyond any reasonable doubt that vacuum fluctuations are real, that they have measurable physical effects, and that quantum field theory provides the correct framework for understanding them. But vacuum fluctuations don't just nudge energy levels and tweak magnetic properties. Under sufficiently extreme conditions, the vacuum can do something far more dramatic. It can produce real particles. In 1974, Stephen Hawking published one of the most celebrated theoretical results in modern physics. He showed that black holes aren't completely black. They radiate, they emit particles, they glow with a faint thermal radiation that has come to be known as Hawking radiation. To understand how this works, we need to think about what happens to quantum fields near a black hole's event horizon. The event horizon is the boundary around a black hole, beyond which nothing can escape. It's not a physical surface. There's nothing there you could touch or bump into. It's a mathematical boundary, a point of no return. If you cross it, the curvature of space-time is so severe that every possible path, even one taken at the speed of light, leads further inward. You can't get out. Now consider the quantum fields near this event horizon. The fields are in their vacuum state, fluctuating as they always do. But the intense gravitational field near the horizon affects these fluctuations in a profound way. The key is that the vacuum state isn't an absolute thing. It depends on the observer. What one observer considers the vacuum, another observer in a different state of motion or in a different gravitational environment might not. Near a black hole, the gravitational field is so strong that it creates a mismatch between what a distant observer considers the vacuum and what's actually happening at the horizon. The vacuum fluctuations near the event horizon, from the perspective of a distant observer, look like real particles being emitted. The gravitational field of the black hole effectively promotes vacuum fluctuations into real excitations of the quantum fields. Fluctuations that would normally remain virtual, remaining part of the vacuum's minimum energy, get converted into actual particles that carry energy away from the black hole. The common popular description says that particle-antiparticle pairs form near the event horizon, one falls in and the other escapes. This is another use of the virtual particle metaphor, and like the general version, it's helpful as a rough picture but shouldn't be taken literally. What's really happening is that the curved space-time near the black hole changes the nature of the vacuum state itself. The vacuum, as defined by an observer far from the black hole, is not the vacuum as defined by the physics near the horizon. This mismatch produces real radiation. The temperature of this radiation depends on the mass of the black hole. More massive black holes are colder. Less massive black holes are hotter. For a black hole with the mass of our Sun, the Hawking temperature is about 60 billionths of a Kelvin above absolute zero. That's unimaginably cold, far colder than the cosmic microwave background radiation that fills all of space. This means that solar mass black holes absorb more radiation from their environment than they emit through Hawking radiation. They're gaining energy, not losing it. For Hawking radiation to dominate, you'd need a black hole that's much less massive than any we've observed. A black hole with a mass of roughly 1 trillion kilograms, about the mass of a small mountain compressed into a space smaller than an atomic nucleus, would have a Hawking temperature of about 100 billion Kelvin. Such a black hole would radiate intensely, producing a torrent of particles, and as it radiated, it would lose mass. As it lost mass, it would get hotter, and radiate faster. The process would accelerate, with the black hole getting smaller, hotter, and brighter until it finally evaporated completely in a burst of radiation. Hawking radiation has not been directly observed. The black holes we know about are all far too massive, and therefore far too cold for their Hawking radiation to be detectable against the cosmic microwave background. Detecting Hawking radiation from an astrophysical black hole would require instruments billions of times more sensitive than anything we currently possess. But despite never being directly observed, Hawking radiation is widely accepted by the physics community. It follows logically from well-established principles of quantum field theory applied to curved spacetime. The mathematical framework is solid, and it's been independently derived using multiple different approaches by numerous physicists over the decades. There is also a closely related phenomenon called the Unruh effect, predicted in 1976 by William Unruh, which states that an accelerating observer in empty space will perceive thermal radiation particles where a non-accelerating observer sees only vacuum. The physics behind the Unruh effect is mathematically analogous to Hawking radiation, and both arise from the same fundamental principle. The vacuum state is observer-dependent. What one observer considers empty, another observer may see as filled with particles. The Unruh effect deserves more attention because it reveals something truly profound about the nature of the vacuum. Imagine you're floating in deep space, far from any stars or planets, completely at rest. The quantum fields around you are in their vacuum state. No particles, just the quiet minimum fluctuations that the uncertainty principle demands. Now imagine you start accelerating. You fire a rocket and begin picking up speed. According to Unruh's calculation, as you accelerate, you'll start detecting particles. The vacuum that was empty when you were at rest is now filled with a warm bath of radiation. The faster you accelerate, the higher the temperature you'll measure. For an acceleration of about 10 to the 20th meters per second squared, you'd measure a temperature of about 1 Kelvin. That's an enormous acceleration, far beyond anything humans have ever experienced, which is why the Unruh effect has never been directly measured. But the prediction follows rigorously from quantum field theory, and it tells us something fundamental. The vacuum state is not an absolute concept. It depends on the observer's state of motion. What counts as empty depends on who's asking. This connects to Einstein's equivalence principle, which states that acceleration and gravity are locally indistinguishable. If an accelerating observer sees particles in the vacuum, and if acceleration is equivalent to gravity, then a gravitational field should also produce particles from the vacuum. And that's exactly what Hawking radiation is. The deep connection between these two effects provides powerful theoretical support for both, even though neither has been directly observed in its original astrophysical or accelerating observer form. There have also been attempts to observe analog versions of Hawking radiation in laboratory settings. In 2010, an Italian group led by Daniele Faccio observed the analog of Hawking radiation in an optical system, using ultra-short laser pulses in glass to create conditions analogous to an event horizon. The results were consistent with the theoretical predictions, though these analog experiments don't prove that astrophysical Hawking radiation exists. They show that the underlying physics, the conversion of vacuum fluctuations into real particles, by horizon-like boundaries works as predicted. The importance of Hawking radiation for our story tonight isn't that it lets black holes glow. It's what it tells us about the vacuum. The vacuum isn't just fluctuating quietly in the background. Under extreme conditions, those fluctuations can be amplified, converted, transformed into real particles with real energy. The vacuum is a reservoir, a source. Given the right conditions, it can produce observable matter and radiation. This idea that the vacuum can serve as a source of real particles under extreme conditions connects to several other phenomena in physics. One of the most striking is the Schwinger effect, predicted by Julian Schwinger in 1951. Schwinger showed that in a sufficiently strong electric field, the vacuum of quantum electrodynamics becomes unstable. The electric field can pull electron-positron pairs out of the vacuum, converting the energy of the electric field into real matter. This isn't virtual particles. These are real electrons and real positrons being created from the energy stored in the electric field, mediated by the structure of the vacuum. The electric field strength required for the Schwinger effect is enormous, roughly 1.3 times 10 to the 18th volts per meter. That's far beyond what any current technology can produce. But the prediction is taken seriously, and there are ongoing efforts to create sufficiently strong fields using high-power lasers. If the Schwinger effect is ever observed in the laboratory, it will be yet another dramatic confirmation that the vacuum is not empty, that it's a medium with structure, with properties, and with the capacity to produce matter when sufficiently stressed. Let's step back and take stock of what we've established. The vacuum, the state we casually call empty space, is filled with quantum fields in their lowest energy state. Those fields fluctuate constantly, driven by the uncertainty principle. The fluctuations are not particles popping into existence. They're inherent variations in the field values, part of the minimum activity that quantum mechanics demands. These fluctuations have real, measurable consequences. They shift the energy levels of hydrogen atoms by a tiny but precisely measurable amount. They modify the magnetic moment of the electron, and the theoretical prediction, including vacuum effects, matches experiment to more than 10 decimal places. They create a measurable force between metal plates placed close together in a vacuum, and under extreme conditions, near black holes or in enormously strong electric fields, the fluctuations can be promoted into real particles. The vacuum participates in physics. It's not a passive stage, it's an active player. It interacts with every particle in the universe, subtly modifying their properties, shifting their energies, altering their behavior. And the evidence for this is not speculative. It's not theoretical conjecture. It's established experimental fact, confirmed by some of the most precise measurements ever made in science. And yet, there's still one more dimension to this story. Because the vacuum's fluctuations don't just affect individual atoms and particles in the laboratory. They shaped the entire universe. The structure you see when you look up at the night sky, the galaxies, the galaxy clusters, the vast filaments of the cosmic web, all of it traces back to quantum fluctuations in the vacuum during the earliest moments of cosmic history. The vacuum didn't just influence the universe. In a very real sense, it created the universe we see. And that's where our story goes next. We've spent this journey exploring the vacuum at the smallest scales. We've looked at quantum fields and their fluctuations. We've examined zero-point energy and the Casimir effect. We've seen how vacuum fluctuations shift atomic energy levels, modify particle properties, and under extreme conditions can produce real particles. All of this is fascinating physics, confirmed by experiment, verified to extraordinary precision. But now it's time to zoom out, way out. Because the vacuum isn't just a laboratory curiosity, it isn't just something that affects atoms and electrons in clever experiments. The properties of the vacuum have shaped the entire universe. The structure of everything you see when you look up at the night sky, every galaxy, every cluster of galaxies, every vast filament of the cosmic web, all of it traces back to quantum fluctuations in the vacuum during the earliest moments of cosmic history. The vacuum didn't just participate in the story of the universe. In a very real sense, it wrote the opening chapter. To understand this, we need to go back to the beginning, not just to the Big Bang, but to what happened in the first unimaginably tiny fraction of a second after it. Because something extraordinary happened during that sliver of time. Something that determined the shape, structure, and fate of everything that came after. The universe we observe today has several striking features that require explanation. First, it's remarkably uniform. When you look at the cosmic microwave background, radiation, the afterglow of the Big Bang that fills all of space, you find that its temperature is almost exactly the same in every direction. It varies by only about 1 part in 100,000. The universe looks the same to the left as it does to the right, the same above as below, the same in every direction to extraordinary precision. Second, the geometry of the universe is flat. Not curved like a sphere, not curved like a saddle, but flat. Parallel lines stay parallel. The angles of a triangle add up to 180 degrees, even on cosmic scales. The geometry of the universe is the simplest possible geometry, Euclidean, the geometry you learned in school. Third, despite being incredibly uniform on large scales, the universe has structure on smaller scales. There are galaxies. There are clusters of galaxies. There are vast walls and filaments stretching across billions of light years, separated by enormous voids. This structure exists. Something seeded it. Something created the initial variations in density that gravity then amplified over billions of years into the galaxies and cosmic web we see today. In the 1980s, physicists proposed a bold idea to explain all three of these features simultaneously. The idea is called cosmic inflation, and it has become the leading theory for the very early universe. The basic proposal is this. In the first tiny fraction of a second after the Big Bang, the universe underwent a period of exponential expansion. Not the gradual, steady expansion we observe today, but an incredibly rapid, explosive expansion that doubled the size of the universe over and over again in an unimaginably short time. How rapid? During inflation, the universe doubled in size roughly every 10 to the negative 37 seconds. That's a decimal point followed by 36 zeros, and then a 1. And this doubling happened many times, perhaps 60 to 70 times or more. Each doubling multiplied the size of the universe by 2. After 60 doublings, the universe would have expanded by a factor of roughly 2 to the 60th power, which is about 10 to the 18th. A billion times larger. And all of this happened in a time span shorter than anything you could possibly imagine. The entire inflationary period may have lasted only about 10 to the negative 32 seconds. What drove this expansion? This is where the vacuum enters the story in the most dramatic way possible. According to inflationary theory, the early universe contained a quantum field, often called the inflaton field, that was stuck in a high-energy vacuum state. Not the true vacuum, not the lowest possible energy state, but a false vacuum. A state that appeared to be stable, but actually had a lower energy configuration available. Think of it like a ball sitting in a shallow depression on the side of a hill. The ball appears to be at rest. It's in a local minimum of energy, but it's not at the bottom of the hill. There's a lower energy state available if the ball can get over the lip of the depression and roll down to the valley below. The ball in the depression is in a false vacuum. The valley below is the true vacuum. The inflaton field in the early universe was in such a false vacuum. It had enormous energy density, energy stored not in particles or radiation, but in the configuration of the field itself. This energy pervaded all of space uniformly, and according to general relativity, a uniform energy density filling all of space doesn't attract things together like normal gravity. It pushes them apart. It causes space to expand, and the higher the energy density, the faster the expansion. The inflaton field's energy density was colossal. It drove the exponential expansion of space, blowing up the universe from something unimaginably tiny to something macroscopic in a fraction of a second. The way inflation actually proceeded is important for understanding the vacuum's role. In the R&B, most widely studied models, the inflaton field didn't jump suddenly from the false vacuum to the true vacuum. Instead, it rolled slowly down a gentle slope in its energy landscape. Imagine a ball on a very shallow hillside, so shallow that the ball rolls almost imperceptibly slowly. While the inflaton field was rolling slowly, its energy remained nearly constant, and this nearly constant energy density continued to drive exponential expansion. This is called slow roll inflation. The expansion continued as long as the field was rolling. Only when the field reached the bottom of the slope, the true minimum of its potential energy, did inflation end. At that point, the field oscillated rapidly around the minimum, and these oscillations transferred energy from the inflaton field into all the other quantum fields, producing a flood of particles. This process is called reheating. It's the moment when the energy stored in the vacuum configuration of the inflaton field was converted into the hot, dense plasma of particles and radiation that we associate with the Big Bang. The universe went from being dominated by vacuum energy to being dominated by matter and radiation in an extremely short time. Everything that exists today, every atom, every photon, every particle of dark matter was produced during reheating from the energy that had been stored in the inflaton field's vacuum state. Regions that were initially close together were flung apart to enormous distances. The universe expanded so fast that any initial curvature was flattened out, like inflating a balloon so large that any small patch of its surface appears perfectly flat. This explains why the universe's geometry is flat. Any initial curvature was diluted to insignificance by the enormous expansion. The uniformity of the universe is explained the same way. Before inflation, the observable universe was contained within a tiny region so small that everything within it could have been in thermal equilibrium. Everything was at the same temperature because everything was close enough to exchange energy. Then inflation stretched this tiny uniform region to cosmic proportions. The uniformity we see in the cosmic microwave background today is a relic of the uniformity that existed in that tiny pre-inflationary patch, blown up to the size of the observable universe. But here's where the vacuum's quantum nature enters and changes everything. The inflaton field, like all quantum fields, had vacuum fluctuations. Even during inflation, even while the field was stuck in its high-energy false vacuum, the uncertainty principle ensured that the field's value fluctuated slightly from point to point. At any given location, the inflaton field wasn't at exactly the same value. It was jittering, varying randomly by tiny amounts. These fluctuations were quantum mechanical. They were the irreducible minimum variations that the uncertainty principle demands. They were microscopic, occurring on subatomic length scales. Under normal circumstances, these fluctuations would be far too small to have any observable effect on anything. But inflation changed that. The exponential expansion of space stretched everything, including these quantum fluctuations. Fluctuations that started on subatomic scales were stretched to astronomical scales. By the end of inflation, variations that began as quantum jitters in the inflaton field had been blown up to sizes spanning millions of light years or more. The quantum had become cosmic. When inflation ended, when the inflaton field finally decayed from its false vacuum to the true vacuum, its energy was released. This energy was converted into a hot, dense soup of particles and radiation. This is what we think of as the Big Bang. The hot, expanding universe filled with matter and radiation that eventually cooled to form atoms, stars, and galaxies. But the matter and radiation produced in this process weren't perfectly uniform. They carried the imprint of the inflaton field's quantum fluctuations. Regions where the inflaton field had fluctuated to slightly higher values ended up with slightly more energy, slightly higher density. Regions where it had fluctuated to slightly lower values ended up with slightly less density. These density variations were tiny, only about 1 part in 100,000, but they were real, and they were everywhere. These variations are the seeds of all structure in the universe. Over the following billions of years, gravity went to work on them. Regions that were slightly denser than average attracted more matter through gravity, becoming denser still. Regions that were slightly less dense lost matter to their denser neighbors, becoming emptier. The tiny density fluctuations were amplified by gravity into the galaxies, galaxy clusters, and cosmic web we observe today. This is one of the most remarkable ideas in all of science. The galaxies you see through a telescope, the vast filaments of the cosmic web, stretching across billions of light years, the enormous voids between them, all of it originated as quantum fluctuations in the vacuum during the first fraction of a second after the Big Bang. The largest structures in the universe grew from the smallest possible variations in the quantum vacuum. The quantum world and the cosmic world are connected in the most intimate way imaginable. And we have evidence for this. Strong evidence. The cosmic microwave background radiation, the afterglow of the Big Bang, carries an imprint of those primordial density fluctuations. When we map the temperature of the cosmic microwave background across the sky, we see tiny variations. Spots that are very slightly warmer or cooler than average. These variations are the direct descendants of the quantum fluctuations that occurred during inflation. They're a snapshot of the universe when it was only about 380,000 years old, showing us the density variations that would eventually grow into galaxies and galaxy clusters. The pattern of these variations, their statistical properties, their distribution across different angular scales, has been measured with extraordinary precision by satellite missions. The Cosmic Background Explorer measured them first in 1992. The Wilkinson Microwave Anisotropy Probe refined the measurements starting in 2001. And the Planck satellite, launched in 2009, mapped the cosmic microwave background with exquisite detail. The results are remarkable. The statistical properties of the temperature variations in the cosmic microwave background match the predictions of inflationary theory with great accuracy. The fluctuations are nearly scale invariant, meaning they have roughly the same amplitude at all scales, which is exactly what inflation predicts. They follow a Gaussian distribution, meaning they're random in the specific mathematical way that quantum fluctuations should be. The pattern we see in the cosmic microwave background is consistent with having originated as quantum vacuum fluctuations stretched to cosmic proportions by inflation. This is extraordinary. We're looking at the sky and seeing evidence of quantum mechanics operating at the dawn of time. The spots in the cosmic microwave background, each one spanning enormous distances, are the stretched out remnants of subatomic quantum fluctuations from the earliest moments of the universe. The vacuum's quantum jitters, amplified by inflation and sculpted by gravity, became everything. Now let's connect this back to something we discussed earlier: the vacuum energy. The zero-point energy of the quantum fields that fill all of space, because this energy has another profound implication for the universe, one that was discovered much more recently and that remains one of the deepest mysteries in all of physics. In 1998, two teams of astronomers made a discovery that shocked the world. They were studying distant supernovae, exploding stars that serve as cosmic distance markers because their peak brightness is known. By measuring how bright these supernovae appeared and comparing that to how bright they actually were, the astronomers could determine their distances, and by measuring the redshift of the light from these supernovae, they could determine how fast the universe was expanding at the time the light was emitted. What they expected to find was that the expansion of the universe was slowing down. After all, gravity pulls matter together. Every galaxy in the universe attracts every other galaxy. This mutual gravitational attraction should be decelerating the expansion, like a ball thrown upward that gradually slows as the gravity pulls it back. What they actually found was the opposite. The expansion of the universe is speeding up, not slowing down, accelerating. Distant galaxies are receding from us faster and faster, not slower and slower. Something is pushing the universe apart, overcoming the gravitational attraction of all the matter in the cosmos. This discovery earned Saul Perlmutter, Brian Schmidt, and Adam Rees the Nobel Prize in Physics in 2011, and the mysterious force driving the acceleration was dubbed dark energy. The simplest explanation for dark energy is that it's the energy of the vacuum itself, a constant energy density pervading all of space, present everywhere at all times, unchanging as the universe expands. This is exactly what you'd expect from the zero-point energy of quantum fields. The vacuum has energy. That energy fills all of space. It should have gravitational effects, and those effects, according to general relativity, would cause space to expand faster and faster. Observationally, Dark energy accounts for about 68% of the total energy content of the universe. It's the dominant component, more than ordinary matter, more than dark matter. The energy of the vacuum, or something behaving exactly like it, is the single largest contribution to the energy budget of the cosmos. But as we discussed earlier, there's a catastrophic mismatch between the predicted value and the observed value. Quantum field theory predicts a vacuum energy density roughly 120 orders of magnitude larger than what astronomers observe. This cosmological constant problem remains unsolved. It's possible that some unknown mechanism cancels almost all of the vacuum energy, leaving just the tiny residual that drives the observed acceleration. It's possible that our understanding of how gravity responds to vacuum energy is incomplete. It's possible that the answer lies in a theory of quantum gravity that we haven't yet developed. Nobody knows. This single problem, the question of why the vacuum energy is so much smaller than our best theories predict, may be the most important unsolved problem in fundamental physics. But even with this mystery unresolved, the basic picture is clear. The energy of the vacuum, whatever its exact value, is shaping the fate of the universe. If dark energy continues to behave as it currently does, the universe will expand forever. Galaxies will move apart from each other faster and faster. Eventually, distant galaxies will be carried beyond the observable horizon. Their light unable to reach us because the space between us is expanding faster than light can cross it. The universe will become emptier, darker, and lonelier. Trillions of years from now, the only galaxies visible from any given point will be those in the immediate local group, bound together by gravity tightly enough to resist the expansion. Everything else will have disappeared beyond the cosmic horizon. The vacuum's energy is determining the long-term fate of everything that exists. But there's another way the vacuum shaped the universe that we haven't discussed yet, and it involves a concept called spontaneous symmetry breaking. In the very early universe, when temperatures were extraordinarily high, the quantum fields existed in a symmetric state. The electromagnetic force and the weak nuclear force, which appear as completely different forces today, were unified into a single electroweak force. The vacuum state at those extreme temperatures was different from the vacuum state today. It had a higher symmetry. As the universe expanded and cooled, about a trillionth of a second after the Big Bang, the temperature dropped below a critical threshold. The Higgs field, which had been fluctuating around zero in the high-temperature symmetric vacuum, suddenly settled into a non-zero value everywhere in space. This was a phase transition, analogous to water freezing into ice. Just as liquid water has rotational symmetry that ice crystals break, the high-temperature vacuum had a symmetry that the new Higgs vacuum broke. When the Higgs field settled into its new non-zero vacuum state, the consequences were dramatic. The W and Z bosons, which had been massless, suddenly acquired mass. The electromagnetic force and the weak force, which had been identical, became distinct. The physics of the universe fundamentally changed because the vacuum changed. The rules governing particle interactions after this phase transition were different from the rules before it. The universe we live in, with its specific forces and particle masses, is a direct consequence of which vacuum state the Higgs field settled into. A different vacuum would have meant different physics, different chemistry, different possibilities for structure and complexity. The vacuum didn't just contain the universe, it defined what kind of universe was possible. The ultimate future of the universe, whether it expands forever or eventually reverses or does something else entirely, depends on the properties of the vacuum. And there's one more possibility we need to consider, one that is speculative but grounded in real physics, and that is perhaps the most dramatic implication of everything we've discussed tonight. It's the idea that the vacuum itself might not be stable. Remember the inflaton field during cosmic inflation. It was stuck in a false vacuum, a state that looked stable but wasn't truly the lowest energy state. Eventually, it decayed to the true vacuum, releasing its energy and creating the matter and radiation that fills the universe. The question is, could the same thing happen again? Could the vacuum we live in today, the vacuum state of the quantum fields that fill our universe right now, be another false vacuum? This isn't idle speculation. There are reasons from real physics to take this possibility seriously. The key involves the Higgs field, the quantum field responsible for giving mass to fundamental particles. The Higgs boson was discovered at the Large Hadron Collider in 2012, confirming the existence of the Higgs field, and measurements of the Higgs boson's mass, combined with measurements of the top quark's mass, allow physicists to calculate the stability properties of the Higgs field's vacuum state. The result is concerning, at least from a theoretical perspective. Based on the measured values, the Higgs vacuum appears to be metastable. Not absolutely stable, not clearly unstable, but metastable. It's in a state that could, in principle, decay to a lower energy state, but the probability of such a decay is astronomically low. The expected lifetime of the metastable Higgs vacuum is far longer than the current age of the universe, probably much longer than 10 to the 100 years. So there's no practical danger, but the theoretical possibility is there. If the Higgs vacuum were to decay, the consequences would be extraordinary and catastrophic. The decay would begin at a single point in space, a quantum fluctuation that pushes the Higgs field over the energy barrier, separating the current metastable state from the true vacuum. At that point, a bubble of true vacuum would form and begin expanding outward at the speed of light. Inside this bubble, the Higgs field would have a different value. And because the Higgs field determines the masses of fundamental particles, inside the bubble, the masses of electrons, quarks, and W and Z bosons would all be different. The laws of physics, as they appear to us, would change. Chemistry would stop working. Atoms as we know them couldn't exist. Stars couldn't form. Life couldn't survive. The bubble of true vacuum would be a region of space where the rules are fundamentally different, spreading outward at light speed, converting everything it touches into a completely different physical regime. And because it travels at the speed of light, there would be no warning, no advance signal. The bubble would arrive at the same time as any light that could warn of its approach. One moment, everything is normal. The next, everything changes. This sounds terrifying, but there are important caveats. The probability is incredibly low. The expected timescale for such a decay is so far beyond the current age of the universe that it's effectively zero for any practical purpose. Furthermore, these calculations depend sensitively on the precise values of the Higgs mass and the top quark mass, and small changes in those values could shift the result from metastable to fully stable. Future, more precise measurements might show that the Higgs vacuum is absolutely stable after all. But the conceptual point is profound. The vacuum state, the ground state of the quantum fields that fill our universe, might not be permanent. It might be a temporary arrangement, a false flaw that could give way to something deeper. The very fabric of physical reality as we know it, the properties of particles, the strengths of forces, the rules that govern chemistry and biology, all of these depend on a vacuum being in its current configuration. If the vacuum changes, everything changes. So let's step back and look at the full picture of what we've explored tonight. We started with a simple question. What is the vacuum? What is empty space? And the answer turned out to be far more profound and far more strange than anything everyday intuition would suggest. The vacuum is not empty. It cannot be empty. Space is filled with quantum fields, at least 17 of them, all stretching across every point in the universe. These fields are the fundamental fabric of reality. Everything that exists, every particle, every force, every interaction, is a manifestation of these fields. When all excitations are removed, when there are no particles present, the fields remain. They're always there, and in their lowest energy state, the vacuum state, they still fluctuate. They still carry energy. The uncertainty principle guarantees that the fields can never be perfectly still. There's always a residual jitter, a minimum vibration, a 0-point energy that persists no matter what you do. This 0-point energy is real. It creates measurable forces between metal plates. It shifts the energy levels of atoms. It modifies the magnetic properties of electrons with a precision confirmed to more than 10 decimal places. Under extreme conditions, near black holes or in enormously strong fields, vacuum fluctuations could be converted into real particles. The vacuum shaped the universe. During cosmic inflation, quantum fluctuations in the vacuum were stretched to cosmic proportions, becoming the seeds of all structure. Every galaxy, every cluster, every filament of the cosmic web traces its origin to a quantum jitter in the vacuum during the first fraction of a second of cosmic history. The evidence for this is imprinted on the cosmic microwave background radiation and matches theoretical predictions with remarkable precision. There's another piece of evidence that confirms the role of vacuum fluctuations in shaping the universe, and it comes from the distribution of galaxies themselves. When the primordial density fluctuations from inflation were imprinted on the hot plasma of the early universe, they set up sound waves, pressure waves that traveled through the plasma at about half the speed of light. These waves oscillated, creating regions of compression and rarefaction, denser and less dense spots. When the universe cooled enough for atoms to form, about 380,000 years after the Big Bang, these sound waves froze in place. The pattern they left behind is called baryon acoustic oscillations. It shows up as a slight preference for galaxies to be separated by a specific distance, about 500 million light years in today's expanded universe. This distance corresponds to how far the sound waves traveled before they froze. Multiple galaxy surveys, including the Sloan Digital Sky Survey and the Dark Energy Spectroscopic Instrument, have detected this pattern in the three-dimensional distribution of galaxies across the cosmos. The signal is exactly where inflationary theory predicts it should be. Baryon acoustic oscillations provide completely independent confirmation that the primordial density fluctuations really existed and had the properties that inflation predicts. Combined with the cosmic microwave background measurements, this gives us two separate lines of evidence, both pointing to the same conclusion. Quantum fluctuations in the vacuum during inflation seeded everything. The vacuum's energy is driving the accelerating expansion of the universe right now. Dark energy, the dominant component of the universe's energy budget, behaves exactly like the energy of the vacuum, and the mismatch between the predicted and observed values of this energy is one of the biggest unsolved problems in all of physics. And the vacuum might not even be permanent. The current vacuum state of the Higgs field may be metastable, a temporary configuration that could in principle decay to a different, lower energy state, changing the laws of physics as we know them. The vacuum is not nothing. It never was nothing. It's the most fundamental state of reality, the canvas on which everything is painted, the ocean from which all waves arise, the silence from which all music emerges. It has energy, it has structure, it has fluctuations, it has physical consequences that span from the subatomic to the cosmic, from the interior of atoms to the large-scale structure of the entire observable universe. And here's what I find most remarkable about all of this. We figured it out. Human beings, living on a small planet orbiting an ordinary star, using nothing but our minds and our instruments, discovered that empty space isn't empty. We measured forces that arise from nothingness. We predicted the magnetic properties of electrons to 10 decimal places by accounting for the vacuum's influence. We detected the afterglow of the Big Bang and found in its patterns the fingerprints of quantum fluctuations from the dawn of time. The vacuum is the deepest layer of physical reality we've ever probed. It's the foundation beneath the foundation. And understanding it, truly understanding it, solving the cosmological constant problem, understanding why the vacuum energy has the value it does, figuring out whether the vacuum is truly stable, these challenges represent some of the deepest questions human beings have ever asked about the nature of existence. When you look out at the night sky tonight, at the stars, at the darkness between them, remember what you've learned. That darkness isn't empty. The space between the stars, the gaps between galaxies, the vast voids that stretch across hundreds of millions of light years, none of it is truly empty. It's filled with quantum fields in their ground state, filled with fluctuations that can never be silenced, filled with energy that shapes the fate of the cosmos. What we call nothing is actually the foundation of everything. The particles that make up your body, the light that lets you see the world around you, the gravity that holds you to the earth, all of it arises from quantum fields. And those fields exist everywhere, even in the emptiest regions of space, fluctuating quietly, carrying their zero-point energy, shaping the universe from the very beginning to the very end. The vacuum is not the absence of reality. It is reality in its most fundamental, most stripped down, most essential form. And the fact that we can understand this, that we can measure it, predict it, and test it, is one of the most extraordinary achievements of the human mind. Empty space isn't empty. It never was. And now you know why.